The one alkene reaction that we had prior to this, from chapter 7, was the addition of HX, where example is HBr, becomes HI or HCl, to an alkene. We said that the product of this is going to be an alkyl halide. We talked about the mechanism of this. You need to remember that the alkene pi system here is a big, comfy cloud of electrons. All of the alkene reactions are going to take place in this electron cloud. For the simple addition of HX, HBr in this case, we said that the pi system might look something like this, and that the first step was going to be simply protonation. This is a strong acid, and it's going to donate the proton to the pi system. Once we get this pi complex, very short-lived complex, is going to rearrange, and we're going to get our final product. Now this can rearrange two directions. It can go down this way to give the secondary carbocation, or it can transfer the proton this way to give the primary carbocation. Now, we said that this reaction was going to occur in such a way that we were going to get the most stable carbocation. Secondary carbocation is more stable than primary. This pathway is simply not observed. This tendency to form the most stable carbocation we'll visit over and over again today. You need to remember the orders of carbocation stability. You're going to see exactly the same thing in radical stability. When we looked at this particular reaction, we said that this particular orientation, where the most stable carbocation was formed, is referred to as MARKOVNIKOV addition. We're going to meet anti-MARKOVNIKOV addition today. Anti-MARKOVNIKOV, you simply go to the other carbon for your substitution. So we're going to have two groups, MARKOVNIKOV addition, where we have the more stable carbocation, and anti-MARKOVNIKOV, where we go to the center that would form the least stable carbocation. You can remember MARKOVNIKOV's rule by counting hydrogens and things like that. The danger with that is that sometimes you have resonance shown that messes you up. I just prefer to think of it as whenever you're going to do it in addition, you always look for the most stable carbocation. MARKOVNIKOV is a tough name to spell anyway. We also looked at the whole concept in terms of a reaction coordinate. And actually, I'm trained as a physical organic chemist, and so reaction coordinates are very close to my heart. But if you think about the process of this pi complex decomposing, you can imagine hydrogen simply sliding over this direction. A certain amount of energy is required to do that. And then you would get, in this case, the primary carbocation. If we did it the other way, if we let our hydrogen slide this way, our reaction coordinate would look like this. We would get the secondary carbocation. The energy required to go from here to this transition state is less. And that's why this is the preferred pathway. You always get the lowest energy transition state. Any questions on the concepts?
So Markovnikov is favored then?
Yes, Markovnikov addition is always going to be favored because it has the lowest energy transition state. All right. Overall, we said the mechanism looks like this. We add a proton, it rearranges, it gives us the most stable carbocation. A halogen then attacks in the second step, and we get the alkyl bromide. Once again, we will call this Markovnikov addition. Now, in the last chapter, we talked about carbocations, and we talked about things that stabilize them, etc. It's in this chapter especially, it's important that we remember all of those things. So let's just review it quickly. Here's a set of very stable carbocations. If we have a carbocation that's adjacent to an oxygen, what happens is we can simply delocalize this electron pair, something like this. We've now transferred the positive charge from the carbon to the oxygen. Oxygen does a better job with positive charges. Think about H3O. Very common sort of thing. Oxygen does pretty well with a positive charge. Chlorine. Again, all these electrons be shared. This transfers the positive charge from the carbon out to the chlorine, and that stabilizes it. The most stable in the group here is going to be the nitrogen, the ammonium ion, ammonium. Think about ammonia, NH4. Very common, very stable species. Nitrogen does a great job of stabilizing carbocations. We also looked at things that were stabilized throughout the ring. My favorite here was benzyl, and again, we've done this exercise many times. Next semester, you should do it a lot. Here we're simply delocalizing the charge from the benzyl carbon up into the 3 ring positions. This makes the benzyl carbocation very stable. In terms of alkyl carbocations, we're all familiar with the ordering. We know that tertiary is more stable than secondary, primary, methyl is very unstable. For the last chapter, I gave you an example where we had a carbocation like this. And I said that was very unstable even though it was tertiary. Well, I did a different drawing of this just to show you that. Remember, carbocations must be planar. They're sp squared. In this particular structure, we've got the ears tied back. So it cannot be planar. It's puckered like this, and that makes it very, very unstable, even though it's tertiary. So when you think about carbocations, what you want to think about is resonance stabilized, number 1. Number 2, tertiary, blah, blah, blah. And number 3, is it planar? Any questions on the concepts here? All right, well, in the handout is the first set of reactions here. We've talked about the first one here, addition of HX. We said that this is Markovnikov regiochemistry. Regiochemistry is the word that we use to describe the region of the molecule where the addition occurs. We know this has a carbocation intermediate, and we can get rearrangements. If you add HBr in the presence of peroxides, you get a different result. We'll see that in a minute. Our addition is anti-Markovnikov. This is a radical reaction, and we don't have rearrangements. We can add bromine, chlorine, or iodine That's X2. When we do that, we get a 1,2 dihalide, and the addition is going to be trans. They're always on opposite sides. HOX. X can be bromine or chlorine. Hypochlorite, oh, you're not familiar with the word, but hypochlorite is Clorox. This is basically just bromine and water. We're going to see that this mechanism is very, very similar to this mechanism up here and this mechanism up here. Very similar. We can hydrate. Again, we get Markovnikov regiochemistry, carbocation intermediate, and rearrangements. We can do this in a more civilized manner using a mercury salt, mercuric acetate, followed by sodium borohydride. Again, we get Markovnikov, but we don't get rearrangements. Much more civilized. We're going to go through each of these. And what you need to do is to be able to look at them and remember the little bits of words that are underneath all of these. Our second set, BH3 and THF, anti-Markovnikov, syn addition, hydrogen and the OH. Simple reduction, hydrogen and platinum. Again, syn addition of H2. Osmium tetroxide or potassium permanganate. Give a 1,2 diol. Once again, syn addition. These things sound a little strange, but chloroform KOH introduces dichlorocarbene. This mixture here introduces carbene itself, and you make cyclopropane rings. Talk about those. And our last group here are the oxidations. We can take a double bond with peroxide and make a cyclic ether called an epoxide. You've heard of epoxy resin. This is an epoxide. We can split it with ozone. We can work it up with dissolving metal, or reductively here, or oxidatively, and get carboxylic acids, aldehydes, ketones, and finally a very brutal reaction here, permanganate. We can split, get things like CO2, acids, and ketones. Now we're going to go, this all sounds overwhelming, I know, but it's all going to make great sense as we finally get through this. So let's go ahead and start. We looked at simple addition of HBr to something like propene. What do we know about that reaction? We know it's going to be Markovnikov regiochemistry. It's going to be a carbocation, and it can rearrange. All right. If we take this very same reaction and we do it in the presence of peroxides, we get a different result. Instead of the 2-bromopropane, we get 1-bromopropane. This is anti-Markovnikov regiochemistry. Now, what are these magic peroxide things? Hydrogen peroxide is H2O2, right? When we speak of peroxides here, we're dealing with either peracids or with an organic peroxide, where these are alkyl groups or something like that. Benzoyl peroxide is what you put on zits. Same sort of chemistry. What happens with a peroxide is that this bond is easily broken. When it does, you form peroxy radicals. So the fact that this reaction gives a different product when peroxides are present tells us that the radical is what's reacting. It's a different total mechanism. All right, let's take our peroxide and let's split it, and let's see if we can figure out what's going on here. When we do split this, we wind up with 2 peroxy radicals. Now, in our pot, we also have HBr. Radicals are very reactive species. A radical is, has this unpaired electron, and that makes it very electron deficient. It has the ability to grab something, really anything, from another molecule, and it'll rip it off with its 1 electron. In this case, it's going to rip off the hydrogen, and it's going to leave a bromine radical. The bromine radical is the thing that's going to add to our alkene. Now again, radicals are very reactive species. Probably the biggest bath of radicals that you might be familiar with is cigarette smoke. When you light tobacco and inhale, the process of pyrolysis breaks lots and lots of bonds, not just peroxy, but carbon-carbon bonds. And you wind up with carbon radicals. These are so reactive that they basically do the same sort of chemistry, but the first thing they bump into. They rip off atoms, that damages membranes, damages cells, and stuff like that. Very, very reactive. Every puff of cigarette smoke is estimated to have 4 or 5 billion radicals in it. It's really a fairly toxic sort of thing. For years and years and years, even though this was known chemistry, the tobacco industry argued that these radicals were not present in cigarettes unless you lit them. And so, whatever. Anyway, that doesn't work anymore. Not for them. All right. What's going to happen here with our bromine radical is that, like I said, it's electron deficient. Remember we said that the pi system here is this big, comfy cloud of electrons. It sees this big, comfy cloud of electrons, and it's going to want one of them. What it's going to do is form a bond with one of the carbons, and it's going to leave the pi system 1 electron short. Mechanism looks something like this. In this case, we have formed a secondary radical. Now, why did we form the secondary radical and not a radical on the primary carbon? Just like MARKOVNIKOV said, we're going to form the most stable species. And it turns out that radicals and carbocations follow exactly the same ordering. So that's the first bit of good news for you, right? Everything you learned about carbocations is going to apply now to radicals. Why do we wind up with the opposite regiochemistry? Well, because in order to form the most stable radical, you have to add to the other carbon. Once we form the most stable radical, that's still a very reactive species. And there's lots and lots of HBr floating around. What this does is rip off the hydrogen from this, here it is, and it leaves behind the bromine radical. Bromine radical finds another alkene, and we do it over and over and over again. It's a radical chain reaction. Any question on the concept here? I have a couple maps here. When we speak of radicals, we talk about spin. Remember, a single electron will have a spin associated with it. This is a spin density map calculated for a methyl radical and a terbutyl radical. And the point of this is simply to show that when we have a simple methyl radical, that the radical spin, that is the electron itself, is associated right here on this carbon in this p orbital. When we have lots of groups attached, the electron is actually delocalized. It's not just on the carbon, but it also appears out here on all of these hydrogens and in some calculations on these carbons as well. So it's delocalized. As you delocalize a charge, it becomes more stable, just like carbocations. Is there any question? In the presence of peroxide, the sentence that you want to remember is we're going to have anti-Markovnikov regiochemistry and a radical intermediate. Let's do some quick problems. Now what you want to do with each of these, you look at your reaction conditions, and you say to yourself, I know this reaction. What do I know? I know it's going to be anti-Markovnikov. I'm going to get an alkyl halide and a radical intermediate. As you look at your alkene, what you want to ask yourself is where is the radical going to form? Because that means that the bromine will be on the other atom. So, we have a primary and we have a tertiary. We're going to form a radical on our tertiary center. That means that the bromine added to the primary center. Once we know where the most stable radical is, this is simply going to pick up the hydrogen from HBr, and that's our problem. Isn't that simple? Go ahead and do these guys.
After this, are you going to ask us to show the radical or just the product?
Well, I mean, I could write a neat question where I say, show the radical intermediate. Yeah, I could do that. So for this guy, we could form a secondary radical, or we could form a radical adjacent to a chlorine. Which of these would be the most stable carbocation? Next to the chlorine. Residence stabilized. Therefore, bromine is going to add here, and a radical will be here. Once we know where our radical is, we simply add our hydrogen, and that's our product. Our next one is very, very simple. We simply propene. We can add the bromine to either the primary carbon or the secondary. Secondary radical is going to be more stable, therefore bromine is going to add here. This is going to pick up hydrogen, and we get 1-bromopropane. And finally, here's our old friend. This is the benzyl position, isn't it? The most stable carbocation would be here at the benzyl carbon. Therefore, bromine is going to add here to put the radical in the benzyl position. Once we've done that, we simply pick up a hydrogen, and there we are. Everything you know about carbocations, you can now apply to simple radicals. See, that even saves space in your brain. Any questions? All right, in our list, the next reaction was the reaction of an alkene with bromine, iodine, or chlorine. Here I'm using bromine. The simple fact here is that the product is a 1,2 dibromide. So we've added both bromine atoms to our double bond. This reaction has a defined regiochemistry. That is, or stereochemistry actually. That is, the two bromines are always on opposite sides of the double bond. So they add trans to each other. We do not get rearrangements. All right, let's look and see what's going on. Remember, our alkene has this big happy pi cloud. Bromine can break its covalent bond here. When it does, it would form Br plus and Br minus. It's very polarizable, and it can do this. The Br plus end of the molecule sees all the electrons here, and it simply adds. When it does, it looks just like our protonated pi cloud. Remember, we had the protons sitting on top. Well, here we have Br plus sitting on top. Now, this guy is going to then react with Br minus to give the 1,2 dibromide. In order to do that, Br minus has to attack this carbon. It has to attack it so we can make a bond, right? This is where the fact that this bromonium ion is large comes into play. Bromonium ion. Bromine is a big atom. Here's the carbon we want to attack. There is absolutely no way that this Br minus is going to make it down this way to attack this carbon. The only clear shot it has is to sneak in on the back opposite the Br plus. So, Br minus attacks this carbon, this bond breaks, and we have our trans 1,2 dibromide. Now that makes sense, doesn't it? Let's look at a little movie. This is going to be the addition of bromine to 2-butene. Step 1. Our bromine is going to attack. This breaks, and we get our bromonium ion intermediate. Remember, this is big. Step 2, Br minus attacks from the bottom, and we get trans 1,2 dibromide. This is our bromonium ion. Once again, it's big. And the only pathway for attack is from the backside. That's why we wind up with our trans stereochemistry. Any questions? Now let's do some simple additions. Once again, you look at this and you say to yourself, bromine plus an alkene. No problem, I can do that. I know I'm going to get a 1,2-dibromide, and the stereochemistry will be trans. On this guy, we're going to have trans addition, but who knows? Because it's going to all be single bonds, isn't it? So it's simply going to be 2,3-dibromobutane. Bromine on each carbon, and it looks like that. When I say a 1,2-dibromide, remember that's not the numbering for the name. That's just the fact that the two bromines are on adjacent carbons. All right, here we have cyclohexene. So our double bond is in a ring. Now we have to do stereochemistry, don't we? We know that when bromine attacks, we're going to get trans addition. Our initial product, therefore, would look like this. But we all look at this and we scream because we know better now. We say, oh my goodness, this bromine is big, and we've got them both axial. That's no good. Therefore, this is very quickly going to undergo ring flip to give the diequatorial. The diaxial actually does form first, but then it undergoes a simple ring inversion to give diequatorial. Here we have a simple cyclopentene with bromine. We're going to put a bromine on each carbon, and they're going to be trans to each other. Here I have one bromine up, one down, and again it's a 1,2-dibromide. Any questions? All right, the next one we're going to do in our sequence is actually very, very similar to this. This is going to be the addition of hypohalite. We're going to use HOBr. You can also use HOCl. Once again, HOCl is just Clorox. What happens here is that HOBr is going to break down. Our bromine is going to add to our double bond to make a bromonium ion. When we get our bromonium ion, instead of Br minus attacking, like we just had in the previous one, HO minus is going to be the one that attacks. Now I'm going to say that this has Markovnikov regiochemistry relative to the hydroxyl group. What that means is that hydroxide is going to add to the carbon on the alkene that would give us the most stable carbocation. So when you see this reaction, what you do is you simply say to yourself, okay, HOBr, I can do that. We are going to make a halohydrin, that's a bromine on one carbon, hydroxyl on the other. The stereochemistry is going to be trans. And the hydroxyl group is going to be bonded to the carbon that forms the most stable carbocation. So very, very similar to what we just saw, except we have hydroxide instead of our second bromine. We also have a simple movie. Oh, to make this in the pot, we actually don't add HOBr, although you can. You can just put bromine in water. That will give you HOBr. But this particular witch's brew is what is typically used in the lab. This is N-bromosuccinimide, NBS, and you put this in wet DMSO. The bond here, the nitrogen-bromine bond, is very easily broken. Nitrogen keeps the electrons, and it gives us Br+. So it's a very nice way to make Br+ in the bond. Remember, Br+ is what's going to add to our double bond to give us the bromonium ion. The sequence. We're going to add, get our bromonium ion. Once we do that, water or hydroxide is going to attack backside. That would give us a protonated alcohol. We quickly lose a proton to get the trans 1,2-dibromide. Very, very similar to what we saw for bromine addition, except that water or hydroxide adds instead of Br-. Our movie, 2-butene again. Same thing is going to happen, I hope. Step 1, we're going to form a bromonium ion. Instead of Br- attacking, however, we're going to let water attack, water or hydroxide, from the backside. This gives us a protonated intermediate. We quickly lose this proton. We have our product. It's a trans, 1 bromo, 2 ol. So just like the other one, except what you remember is that hydroxide or water is going to add to the most stable carbocation. Now why? This is what the bromonium ion might look like. Okay? This is not a symmetrical intermediate. Simply because these 2 carbons that were the alkene carbons are going to distribute the charge in such a way that they can stabilize it best. That means that most of the positive charge is going to be on the secondary carbon and less on the primary. Because there's more charge here, water or hydroxide will attack that carbon, and that's why we get Markovnikov regiochemistry relative to the OH group. So once again, saving space in your brain. This is just like our bromine addition, except we add OH minus. Let's do some. Step 1, you look at it and you say to yourself, which of these is the most stable carbocation center? Because that's the one that's going to get the OH. We have a secondary and a tertiary. The most stable carbocation is our tertiary. So the OH is going there, the bromine will go to the other carbon.
Are you recording, Dr. Young?
Yeah,
Good, good.
I hope so.
Me too.
Our next one here, just to make it interesting, I put in HOCl. You look at this and you say, which of these is going to be the most stable carbocation? We have a primary, we have a tertiary. Clearly, the tertiary center is our most stable carbocation. That is where the OH group goes. And the bromine goes to the element. Chlorine. Our next one. Look at our molecule. Secondary carbocation, or tertiary carbocation. Tertiary center, more stable. That is where the OH group goes. And bromine goes to the other one. Now here we have to show stereochemistry, don't we? We know that they're going to be trans, so bromine's going to be up, the OH group on the opposite side. These guys must be trans, OH group on the tertiary carbon.
So you mean you wanted okay, so you want some wedges and some stuff showing in the back, or just, does that show you?
This shows it right here. That's good enough. All right, any question on these guys?
Dr. Young, is that also showing, when you draw like that on a site, 1, 2, 3, 4, on that site glow, I can't think right now, is that also telling me if these, no, the one down below it, is that also telling me like how the stereochemistry is, if it's going up or down?
But remember, you would get a racemic mixture here. Because our bromonium ion can form on either side, and water could attack from either side. So the only thing that you really know is that these guys must be trans. All right, our next reaction. Plain old acid-catalyzed hydration. Now this is a somewhat brutal reaction. I think we actually do this one in lab. Where we're going to take a double bond. And just like we did with HBr, we're going to take strong acid, we're going to protonate our pi cloud. Except we don't have Br minus around, or a nucleophile, do we? What do we have? We have water. So, going to be just like the addition of HBr, except instead of adding the halogen, we're just going to add the OH group. Just like the addition of HBr. This is going to follow MARKOVNIKOV'S rule. We're going to have exactly the same carbocation, and we can get exactly the same rearrangements. Once again, saving space in your head. Our water, once again, is going to add to the most stable carbocation, but we can also get rearrangements. We have a movie. The steps. We are going to form our pi complex. That will give us a carbocation. Instead of Br minus attacking, here water simply attacks, loses a proton, and we wind up with the MARKOVNIKOV alcohol. Step one, we protonate our pi cloud, and we form the most stable carbocation. Right here, our tertiary center. Step two, the water is now going to attack from either face. I have it coming in the top. This is going to lose a proton. And we wind up with the tertiary alcohol. So, once again, even though these all sound different to you, or look different, it's the same sort of stuff over and over again, isn't it? All right, let's do some. You need to look at these and say, what's going to be my most stable carbocation? You need to realize that this could rearrange. Then you simply add the OH to make the alcohol. Our most stable carbocation is going to be in our tertiary center. Once we form that, OH will add, and that's our product. In our next one, we have a primary center, we have a tertiary center. Our carbocation will be on our tertiary center. That means that OH will add and make the tertiary alcohol. And our last one here, we have a cyclopentene. Now, each of these are secondary carbons, right? But our most stable carbocation is going to be at our tertiary center. So just like with the addition of HBr, initially we would form this carbocation. However, this is going to undergo a 1,2 hydride transfer to give us the tertiary carbocation. Once we have our most stable carbocation, OH minus adds, and we get our alcohol. So addition, give a carbocation, rearrangement, Markovnikov regiochemistry. Any questions? All right, like I said, this is a very, very brutal reaction. It's ugly. But you can do hydration of a double bond in a much more civilized way using a very toxic reagent. And that's going to be mercury. Now we all know that if you eat too much tuna and stuff like that, full of mercury, and it's bad for you. The reason that it's bad for you is that it can form organic mercurials, actually with the alkenes in your body. And remember, all fatty acids are full of cis alkenes. So it's bad stuff that can really mess you up. Nonetheless, if you do hydration using mercuric acetate, we do get Markovnikov regiochemistry, but we do not get rearrangements. Well, that's nice. The way this happens, step one, mercury, our mercury ion here, acts just like the bromonium ion did, just like Br+. Remember, Br+ added to our pi system to form this cyclic intermediate. Well, so does mercury. So again, it's the same concept. Once we've made this intermediate, our charge distribution is going to be slightly different on each of these two carbons. So most of the positive charge is going to be on our tertiary carbon here. So in step two, hydroxide is going to attack. This is going to ring open to give us the organic mercurial. This is, again, the same sort of chemistry that can happen if you eat too much mercury. And it makes you really stupid and stuff like that. All right, our mercury bond here is actually fairly stable. And we've got to somehow get rid of our mercury now. We do that in a second step with a reagent called sodium borohydride. Borohydride simply donates an H- to this point. You don't need to know that. Cleaves the mercury-carbon bond, and we wind up with our simple Markovnikov alcohol. So you always see this reaction shown as two steps. Step 1, mercuric acetate. Step 2, sodium borohydride. The thing that I hope grabs you is that this is exactly the same sort of thing we saw with the bromonium ion, isn't it? And that's the same reason that we get Markovnikov regiochemistry. Again, this carbon shares more of the positive charge than this one. Let's say that your entire grade in organic chemistry depended upon making this alcohol, right? Well, to make it worse, what if I said you had to start with this alkene? You would look at this and you would say, all right, just looking at this bond here, we have Markovnikov regiochemistry, don't we? That is, the OH is on the tertiary carbon, not the secondary. But we've done this enough, we know that this is a benzyl position. And if we try to make a carbocation up here, by gosh, it's going to rearrange to give us the benzyl carbocation. So this should scream at you. I need Markovnikov regiochemistry without rearrangement. Therefore, I want to use mercuric acetate followed by sodium borohydride. Any questions?
So it will go to the, so it will it go to a resonance stable?
Nope.
It will not,
Does not rearrange
does not rearrange.
because we have the mercurinium ion, just like the bromonium ion. We don't have a carbocation. All right, our next group. Starting here with BH3 and THF. This is going to give us anti-Markovnikov alcohols. We are going to add a hydrogen and the OH on the same side. That's syn addition, or cis. And again, there's no rearrangements. Yeah.
Refresh my memory, what's regiochemistry?
Regiochemistry is just the region, it's a word describing the region of the molecule that the reaction occurs. In this case, it's the relationship between the things that you add. So regiochemistry here, anti-Markovnikov, simply means that we've added to the alkene in such a way that we're bonded, the OH is on the carbon that would form the least stable carbocation. Hydrogen and platinum. Simply, we're going to add H2 on the same side. Osmium tetroxide and KMNO4 will make 1,2 diols, again, on the same side. And these guys were making cyclopropanes. So let's start up here with BH3 and THF. This is known as hydroboration oxidation. What you do in hydroboration is we're going to react to give an anti-Markovnikov alcohol, and OH and hydrogen must be on the same side of the molecule. Okay? Anti-Markovnikov, cis addition. Our most stable carbocation would be here. With this reaction, that means that the OH is going here. Now the way this happens, it's a concerted reaction. The BH3, this boron-hydrogen bond, just kind of comes and sits down on the pi system. Remember, think of the pi system as a big cloud of electrons. So it comes and sits down on it. When it does, it's going to be slightly asymmetric, isn't it? And the carbon of the double bond that can accommodate the charge will have the most of the positive charge. So it's like our pi complex, really. Except with BH3, H minus now goes to the carbon that would be the most stable carbocation, and the boron goes to the other guy. We wind up with an organic borane. But the boron and the hydrogen are on the same side. It must be because this all happened at once. It's a concerted reaction. Move the hydrogen up, move this bond down. Step 2. Just like we had a problem getting rid of the mercury, we have to get rid of our boron now. And we do that simply by adding peroxide. You don't need to know the mechanism, although I think it's in the book. It simply cleaves off the boron, and the oxygen is in exactly the same place that the boron was. So bottom line, we have made an alcohol, anti-Markovnikov regiochemistry, and they're on the same side of our molecule.
We're not going to need that for the exam, are we?
Of course. All right, everyone likes a movie. We're going to take our methylcyclopentene. BH3 is going to come sit. Again, it's a pi complex. Hydrogen goes to the carbon that would be the most stable carbocation. And then finally we get rid of our boron. Doing it just with a simple ethene. Step 1. Here comes our BH3. You see, everything happens at once. That's why they're on the same side. Once we got this, we simply do oxidation with peroxide to convert the borane intermediate into the alcohol. Anti-Markovnikov regiochemistry, and it's syn or cis addition. Go ahead and do these guys.
On these problems, Dr. Young, I just know where to put the OH. So,
What you do is you look at it and you say which carbon is going to be the most stable carbocation. That's where the hydrogen goes. And the OH will be on the other one. The real challenge here, of course, is drawing a structure. It's a simple bicyclic compound. This is a tertiary carbon, that's a secondary. Our most stable carbocation would be here, wouldn't it? That means the hydrogen from BH3 goes here, and the OH will go to the other side. We must add the hydrogen and the OH on the same side of the molecule. So it kind of looks like this. Anti-McCormickov, syn addition. Now this is actually the favored product. You could have drawn it with the hydroxyl group facing down, but that's not favored. Using your vast intuition of organic chemistry, why not?
There's no.
It's a it's a steric thing, it's a size thing. Again, you've got to add this boron and you have to do all this stuff. You have two possibilities. This guy has one carbon bridge sticking up. This bottom half would have a 2-carbon bridge. The 1-carbon bridge is smaller. So it goes where it fits the easiest. On the exam, if you had done it the other way, that would be fine. All right, this next one. Secondary carbocation, tertiary carbocation. That means the hydrogen's going to go here, the OH group here. Don't have to worry about stereochemistry because it's all single bonds. All right, following up now on additions that occur on the same face of the molecule. Let's look at probably the simplest of the alkene reactions, and that is catalytic reduction. What you do here literally is you have your alkene, usually in a solvent of some sort, alcohol. You have platinum, and the platinum is deposited as a very, very thin atomic layer, usually on something like charcoal. So you take and you add a teaspoon of your platinum charcoal, and then you bubble in hydrogen gas. When you do that, you go from a double bond to a single bond, and hydrogen that adds comes on the same face of the molecule. This is how you take good healthy corn oil and make margarine. You take the double bonds in fatty acids, hydrogen, platinum catalyst, bubble it up until it thickens up as much as you want, shut off the hydrogen, clean it up, got to get the black stuff out. And then you have your saturated fat. In the process here, you also generate the trans fat, which is the really bad stuff. All right, what's happening here? Step one, when you take hydrogen and platinum, this works with platinum, palladium, all these heavy rare metals. Hydrogen will adsorb to the surface. Now what that means is it comes in and it sticks. When it sticks, it actually breaks the bond here between the hydrogen atoms, and they become bonded adjacent to each other to the platinum surface. So we have two hydrogens now just sticking up. Step two, our alkene with its lovely pi system also comes in, sees this happy surface, and it sits down on it. These guys slip and slide around the surface until they find each other. And when they do, both hydrogens add to the double bond at the same time. Because of that, this is why we get our cis addition. As soon as we do that, there's no more pi system, so this stuff flies off the surface. What you have to remember is simply cis addition. We get rid of our double bond, both hydrogens on the same side. Any questions? And let's do it. If this was an exam sheet, you would look at this and say, okay, hydrogen gas and platinum. I know that. I'm going to convert my double bond into a single bond. I'm going to put hydrogen on each carbon, and they're going to be on the same side. Here, it doesn't matter, because it's all single bonds, so you just draw the alkene. Now it matters.
That was nice.
Once again, we have to somehow draw the bicyclic thing. But we know that both hydrogens, our little blue guys, are going to go on the same side, and our double bond is going to become a single bond. Once again, I put them on the top because this is less crowded than the bottom is. And finally, we have two methyl groups in our cycloalkene. Hydrogens must go on the same side. Therefore, we get this as our product. Two hydrogens on the same side. Is this molecule chiral? Does it have chiral centers?
I don't think so. Sure does.
1, 2.
These two.
Is it a meso compound?
Oh, that's what I was
Sure.
thinking.
Absolutely, it's a meso compound. So it has chiral centers, but it's not chiral as a molecule. All right, speaking of things that happen on the same side, we can also make 1,2 diols. These are called glycols. Everyone's heard of ethylene glycol. Glycol simply means 2 hydroxyl groups next to each other. You can make this 2 ways. Both of these reagents have very, very similar mechanisms. They differ in the fact that osmium tetroxide is extremely toxic, extremely expensive, but organic chemists like that. So lots of people use this stuff. It also takes 2 steps. You have to react it with the osmium, and then you have to add bisulfite to get rid of the osmium. With potassium permanganate, it's cheap, dirt cheap, literally. The yield is just about the same. It's also very nice, nicely colored as purple. And you know when the reaction's over because it goes from purple to ugly brown. What's happening here is our alkene is going to react with either the osmium tetroxide or the manganate to form an intermediate ester like this. Both of these oxygens, these are the ones that are going to wind up as hydroxyl groups, come from the MnO4. Now again, what's happening here is our pi cloud, big squishy pi cloud full of electrons, simply reacts with the MnO4 minus. This adds to both carbons, and we form this intermediate. With osmium, this is a stable intermediate, and you have to add bisulfite. With permanganate, you don't. This will spontaneously break down to give the 1,2 diol. Because they both come from the manganese, they have cis stereochemistry. So, preserving space in your brain. Hydrogenation. Both hydrogens, same side. Formation of 1,2-diols. Both hydroxyl groups, same side. BH3, hydrogen in the hydroxyl group. Add it once, same side. Go ahead and quickly do these. We have an ethyl cyclohexene. Osmium tetroxide and permanganate, same basic mechanism. We are going to make this into a 1,2-diol. Hydroxyl groups will be on the same side. We have to show that somehow. That would work. I just used wedgies. You could, of course, draw a cyclohexane ring and just make sure that your two hydroxyl groups are either both equatorial or both axial. Here we're using permanganate. Same reaction. We're just going to convert this into a 1,2-diol with the hydroxyl groups on the same side. Any questions? All right, let's do carbenes and then we'll take a quick break. Carbenes. Carbenes are strange things. A carbene is a carbon with two unpaired or unshared electrons, empty p orbitals, and it's just extremely reactive. We can make dichlorocarbene simply by taking chloroform and KOH. What happens is the KOH will remove HCl. When it does, it's a carbon with two chlorines. Now this is a very reactive thing. The dichlorocarbene here will simply add to our pi system. It adds simultaneously, and when you're done, you're left with a cyclopropane with two chlorines on this carbon. The other way is that you can make carbene by itself. There are two ways. You can do this mix. This is diiodomethane with zinc copper amalgam, usually in ether. This mixture generates this guy, which is just CH2, carbene itself. And this, just like dichlorocarbene, sits down on the pi system and gives you a cyclopropane. The other way you can do it is to use this stuff. This is called diazomethane. Here you can easily see this is the chunk that's going to become carbene and simply is added to the double bond. Carbene, once again, looks like this. It's an sp squared carbon. It has an unshared pair of electrons and has empty p orbitals. Very reactive thing. This is neutral though, isn't it? Think about its formal charge. It gets one electron from each double bond, counts those two, comes in with 4, and it's still got 4. So it's neutral, but it's extremely reactive. I have a movie here. Step one, we're going to pull HCl off of chloroform to make dichlorocarbene. This is going to come and sit down on the pi system, and we wind up with our product. Once again, this is what dichlorocarbene looks like. Step one, we're going to lose HCl. This is our dichlorocarbene now. Step two is simply going to sit on the double bond. Bonds are made all at once, and you get your product. Any questions? What you have to do is be able to recognize, are you making dichlorocarbene or are you making carbene itself? Remember, chloroform is going to give us dichlorocarbene. Either this or diazomethane will give us carbene itself. All you have to do is draw this thing and then somehow squeeze a cyclopropane on it. So our cyclopropane is going to bridge these two carbons and would look like that. This is going to give us dichlorocarbene. So our cyclopropane carbon, like this one, is going to have two chlorines on it. Going to add to these two carbons, and would simply look like that. Any questions? All right, let's take a quick break, and then we'll come back and do oxidations.